Now we have a very interesting presentation, as the two previous ones and the ones that will follow too. But this one is the Primal-Dual algorithms for order fulfillment at Urban Outfitters, Inc. And we have Dr. Vivek Farias from MIT and Aryan Koyak from Select. So please help me welcome them.
So let me begin by just saying how excited we are to share this work with you here. As an academic, first and foremost, this has sort of been a very, very interesting journey for me personally, because we got to sort of start with something that truly was kind of just a concept, and then work from that concept to something algorithmic, to then building software around it and seeing if the software actually made a difference in practice. What I thought we'd do is use the 30 minutes to maybe walk you through a little bit of that journey and give you a sense of what we did. Just in terms of sort of giving credit where credit's due, whereas it's Aryan and myself presenting here today, it sort of really takes a village. And, in going from that concept to actually building something that actually works, frankly, the real heroes of the story are actually at the bottom. So specifically, at Urban Outfitters, Dave Hayne, who's Chief Digital Officer, is the guy that actually spurred us to think about this to sort of begin with. The engineering teams over there have been phenomenal in actually kind of taking this out of the primordial ooze, so to speak, and making it real. And then at Select itself, where I'm very happy to spend some of my time, Yingzhang Wang and his team, Aryan's on that team, have been sort of crucial in actually, again, making that leap from what's a simple algorithmic idea to something that a large retailer or several large retailers might actually trust in practice. So with that said, let me just sort of get in with really the motivation of this whole thing, right? Depending on who you talk to, there's this notion of kind of the retail apocalypse that we have Amazon, and Amazon's going to eat everyone's lunch, and that's that. So if you're not Amazon, start worrying, right? So there's a grain of truth to that, but it's not necessarily all true. So over here, right, these are actually numbers for Walmart, and Wall Street's been rewarding Walmart very heavily for these numbers. If you look at the numbers in and of themselves, there's in general fairly good news over here until you kind of dig under the covers for a little bit. So the good news is, right, despite the scale of Walmart as an organization, right, there's robust revenue growth. Right, that's the second row over here. If you look at where that revenue growth is coming from, some of it's coming from retail stores, right? That's the fourth row on this slide. But if you compare that with what's actually happening in e-commerce, right, it's sort of a tale of sort of two dynamics, right? In particular, if you look at the second quarter of this year, the year-over-year in-store sales growth was 3%. At many retailers, that number is even lower. It's flat, or sometimes even negative. But e-commerce growth was 30%. If you compare that, by the way, to what that growth, year-over-year growth was in Q2 2018, which is the last column on this slide, that year-over-year growth was 28-point-something%, right? So not only is it growing by these strong double digits, the growth rate appears to also be accelerating. And in many ways, that's why the street is so happy with Walmart and many other retailers that can kind of show numbers like this. The downside of this is the following simple equation, right? Which is that the money you put in the bank is revenue minus cost of goods sold minus cost of fulfillment. And when it comes to this e-commerce growth, right? If somebody walks into your store to actually go buy something off the shelf, your cost of fulfillment consists of, well, the associates working at the store and a whole bunch of other things. If you amortize that out correctly, you're looking at something that's well under a quarter, well under 25 cents, okay? On the other hand, if you look at how much it costs to actually ship that one order to someone, right? It's an order of magnitude off, right? It's several dollars, $3, $4, $5, something like that. And so whereas the double-digit growth is great, the margin on this double-digit growth is actually tremendously painful. Okay, and so that was kind of our motivation going into this. All right, if we're going to see this massive sort of e-commerce growth, how do we make that massive e-commerce growth sustainable and profitable? For sort of large brick and mortar retailers. And so the concept behind it is actually really simple to explain. Okay, so the concept we're trying to go after is actually fairly simple to explain. And I wanted to kind of explain it with this little picture over here, right? So think of this as a caricature of your typical brick and mortar retailer, okay? So what I have on the left, right, are the brick and mortar retailers, sort of, well, brick and mortar stores. Okay, that's stores 1 through N, as I've kind of marked them out. And then finally, this one large sort of e-commerce DC or fulfillment center, okay? And let's imagine that we're looking at like one product, okay, just for this mental model, right? So we're looking at one product, and in fact, you have the best sort of predictions in the world, and it turns out that, the demand for that one product at each of these N stores is some number lambda, right? And the demand, in the e-commerce channel is some multiple of lambda, okay? So what would you do? Well, for economies of scale and so on and so forth, you might say, well, I'd like to serve all these e-commerce orders out of an e-commerce DC, right? So I'll place enough inventory in that DC to essentially serve e-commerce demand. And then I'll place enough inventory in the store as well to serve that demand. And, the structure of sort of the margin structure is such that you will want to carry some sort of safety stock, right? Most of these retailers still operate, especially in apparel, will still operate in that kind of regime. So in this picture, you can think of the gray boxes as corresponding to your expected demand, and the red boxes as corresponding to perhaps the safety stock you're going to carry. So you do that, and then your sales season comes along, and you sell a whole bunch of stuff, and this is maybe where you land up. Okay, so store 1, you're left with the red 1 unit of inventory. Store 2, demand didn't quite realize the way you expected it to. And store 3, you actually sold out entirely, right? Who knows, maybe you even lost some sales there, it's unclear, right? So that's sort of the setting, and we're left with, shall we say, a whole bunch of inventory that's sort of unsold, right? And that inventory is going to scale like sort of the number of stores that you actually have, which is to say there's a lot of it, okay? So there's a lot of that stuff that's actually unsold. So what do retailers do with that? Well, quite simply, it's either marked down or salvaged, right? And it's going to be marked down over some period of time. And after it doesn't work, in that location, maybe it actually gets moved to a different channel or something like that, right? Now, this is where sort of our conceptual idea comes in, which is that, hey, what if you were able to somehow over time, right, pool all that brick and mortar demand together, okay? If we somehow were able to pool all that brick and mortar demand together, and I sort of think about really what we're sort of left over with in this picture. What we're left over with may have actually been enough to actually serve all of the e-commerce demand for this retailer in the first place. Okay, so saying that differently, right? What we'd somehow like to do is proactively use this inventory, right, that we're seeing in these stores in other channels, right? And why do we want to do that? We want to do that because ultimately the idea would be that what this would enable is, if coming back to that sort of profit and loss equation here, a reduction in the cost of goods sold. Okay, that is to say, I'm actually able to serve all of these channels together with fundamentally less inventory. Okay, now that's sort of a very high level motivation. But if you kind of dig into it, right? Well, what are sort of the positives? What are sort of the negatives? How can you do this correctly? And on the flip side, conversely, how can you mess this up, right? So here's how we could do this correctly, right? So one of the opportunities is, hey, if you shipped proactively out of the right store, right, you might actually be able to use up inventory that would not have sold. So put it a different way, if you look at this picture over here, if I realized that, store 2 was going to be left with, like, well in advance, right, that store 2 was going to be left with these 2 units of inventory, hey, I could have made those 2 units of inventory available in a different channel. So as opposed to taking the hit with respect to markdowns and stuff like that, I've now deployed that inventory profitably to sort of a full price e-commerce order. That's the upside, right? But you can immediately equivalently point to the downside. The downside is in store 3, right? Store 3 already sold out. What if you got really excited about store 3 and started shipping e-commerce orders out of store 3? well, then you're going to take a hit and lose sales altogether. So somehow or the other, right, we do want to kind of enable this sort of virtual pooling idea, but it's fraught with risk, right? And that risk boils down to, on one dimension, right, understanding where it's safe to sell product, send inventory out of a store, and where it's not safe. That's one dimension. And then there's a whole bunch of other dimensions that, as you start thinking about this, you can dig into, right? Another dimension immediately is, hey, listen, if you're going to start shipping out of stores, you're going to pay more to ship that stuff out than you would in sort of from one of these e-commerce DCs. So how do you actually manage to ship it out of a store in a manner where it's profitable? You can keep thinking about that and say, well, yeah, maybe what you could do is if you're shipping it from close by, the delays are really small, right? And that drives your customers to come to you, and in fact lets you charge maybe a premium for the delivery. So as you can look at, as you look at this, it's a bit of a multi-objective problem. On the one hand, we deeply care about this pooling issue that I'm talking about. On the other hand, there's a whole bunch of other things we care about that correspond to delivering things cheaply, delivering things on time, and so forth. Okay? So you could ask, well, listen, ultimately what I'm talking about over here is essentially shipping from stores. That's effectively what I'm saying, right? And we've been shipping from stores for about 11 or 12 years now. Okay, so it's fair to ask, well, what is state of the art? Because pretty much 90% of retailers today have implemented some sort of order management system which has logic embedded in it to decide whether to ship from store or not. So if you actually look at what state of the art actually is, it's effectively greedy. Okay, that is to say, you have some sort of cost function that can care about a whole bunch of different things. It can care, it can value how close the store is to the order, how much it costs, how much inventory is left, so on and so forth. But it's fundamentally greedy, okay? And you can ask yourself why fundamentally greedy, right? Like, what's the challenge with this being greedy? And we'll sort of dig into that later, but just, at the highest of levels, it's because you want to get this done quickly, right? You will typically, and Aryan will talk about this later, you'll typically have milliseconds to make a decision. So ultimately, the constraints you actually have to actually get this to run are fairly limited. So that's actually greedy, and the question is, what's the outcome of doing this? This picture will make more sense later in the talk, but it's sort of a stark visual example of what can go wrong with greedy. What I'm showing you over here is a simulation inspired by effectively real data on what happens if you run greedy against this sort of supply network. And remember, the supply network consists of both stores and DCs. And anytime you see a red dot, you should think of this as a spot where you actually had a lot of lost sales. You actually aggressively shipped out of a location, and in fact, you shouldn't have. Okay? This is greedy. As you can see, some of the dots are blue, but it's sort of red all over the place. And it turns out that what we'll be able to do is make that entire picture blue, while worrying about a whole bunch of other metrics, shipping costs, so on and so forth. Okay? So, put a different way, what this is going to be about is, number one, an algorithmic approach to this problem with rigorous, in fact, optimal guarantees. So shall we say, the theorist in me is happy. What's more interesting is that in practice, when we actually look at this run, it comes very, very close to matching a perfect pooling benchmark. Okay? And that's what sort of is kind of really exciting about this. We'll talk briefly about an implementation. It's a massive software implementation that scales to well over 10,000 orders a minute. That corresponds to basically 6 milliseconds per decision. Whereas I'm talking about Urban Outfitters here, they helped us conceptualize this whole idea. This has already been generalized to a whole bunch of other retailers, and I'll talk about how it's been generalized and maybe even have a little bit of a clip with respect to that. So with all that set up out of the way. Let me just actually get into something concrete. A problem formulation. So the problem formulation ultimately is super simple. Okay, really, really simple. Right? What's the formulation? Let's just think about a single product for a second. Right? The single product. I have J supply nodes for that product. These are your stores and your DCs. Okay. I have T order arrival epochs. Right? So the orders can arrive over T periods of time. And I start with some amount of inventory of this product in any given node. Okay, I'm calling that S sub j. And the way to sort of think about how this game gets played forward every time an order arrives, it's associated with a reward vector, right? That reward vector tells me, well, how attractive is a specific node for a specific order, okay? And once I write that down, well, I'm left with sort of a simple sort of integer program, right? After the fact. If I knew all of the orders after the fact, I'd be left with this sort of simple matching type problem, right? That problem is trying to tell me, hey, what you got to do is, assign orders to nodes in a manner that respects the inventory constraint that you have, and you want to maximize reward. And hopefully in maximizing reward, that kind of covers really all of the different objectives that you actually care about, okay? So once you write this, there's a natural first thing to try. And by the way, when we were doing this, we weren't trying to write a theoretical paper. We were trying to solve a real problem. So the first thing we tried was, hey, in the world of revenue management, right, there's a very simple schema to go from something like this to something you can implement. And that schema is, at the current point in time, just have some prediction of what's going to happen going forward, right? So I'm sitting here at time little t. I use my favorite model to come up with a prediction for what these rewards are going to look like going forward the rest of the time horizon. I solve what's effectively a linear program or an integer program or something like that. I use that to come up with a decision for what I do at time t, and then I rinse and repeat. I just roll this story forward, right? So you could do that. It's a very natural thing to do. And in fact, my colleague Steve Graves and Jason Asimovich, who's now at Penn State, tried using this exact same idea in the context of fulfillment for Amazon, okay? So it sort of seems to make sense that this is the right place to start, right? Just rinse and repeat. And surprisingly enough, the schema performed quite poorly for the problem we were thinking about. And after the fact, it's kind of obvious why it performed poorly. Whereas in the Amazon setting, you have let's say 100 odd fulfillment centers where really Amazon's only fulfilling the high volume products out of those fulfillment centers. We're interested in a problem where, remember, we're looking at stores plus DCs. So even a run-of-the-mill retailer has a total of 1,500 odd nodes, right? And the volume of demand you're shipping out of those nodes is in the ones or twos, the single digits. And that really kind of throws this sort of schema for a loop, right? So put more concretely, right, in the Amazon setting, maybe you're actually, even at the smallest sort of levels, you're looking at scales of 144 units a week out of a single FC. In our setting, we're kind of interested in 1 or 2 units a week, and sometimes even smaller than that, okay? So what do? Right? If you can't actually predict this moving forward, and remember, you want to build a software system, right? So hard to stop a software system mid-flight that's in real time to say, oh, I need to adjust a forecast. Can't do that, right? So what do? So what we thought we'd do, because we couldn't get this to work, and it's not like we had huge hopes for this, but we thought we'd try it nonetheless, was actually, as opposed to kind of building a stochastic model of demand, to take a more adversarial view of things, okay? And so the idea with the adversarial view, right, was to sort of say this. Let's just imagine that nature is actually feeding us these reward vectors, right? Nature can be fairly adversarial with respect to what we're trying to do, but we'll control, how the extent to which nature can mess with us in some sort of reasonable way, okay? So what was that adversarial model? Broadly speaking, it has to be an adversarial model on this reward vector, right? On the reward at a specific node, RTJ. And really, the way we think about this is it consists of 2 parts. So first off, right, there's this sort of ZTJ over here that sort of simply encodes whether for any given order, you can actually send that order to a specific node or not. So what does that mean? If somebody comes in to purchase something in a store, right, by definition, you have to give it to them at that store. So ZTJ would be 1 at that store, and it would be 0 for all the other stores, right? There are other reasons, that you might want to have this ZTJ in here. A store suddenly gets shut down for whatever reason, so on and so forth. The second component, the R bar TJ, sort of controls the relative value, of different nodes over time, right? And what we're going to do, and this is where we sort of constrain nature, is we sort of say that, hey, listen, right, the variation in this reward over time can't be too large. And we're going to control that too large by this parameter kappa over here, okay? Turns out that kappa is actually a very natural parameter to actually think about. Specifically, if you set kappa equals 1, you're actually left with a very well-studied matching type problem in the literature referred to as the AdWords problem. And the interesting thing, by the way, about the AdWords problem as an aside is that's a problem that's canonical to how Google effectively matches incoming impressions with ads, right? Again, a setting where building a fine-grained forecast is potentially not that easy. Now, in our setting, kappa is not 1. We want kappa to be general, right? Kappa equals 1 is not that interesting for us. And so a natural question that raises is, how good can you actually do with a general kappa? So over there, right, and this sort of sets up how well you could possibly do, right? One can show that really no algorithm, right, online, randomized or otherwise, can do better than a competitive ratio of 1/1 plus log kappa, right? Competitive ratio being, you can sort of think about this in this setting as, to what extent do I capture the perfect pooling benchmark? That's really how you should think about this, okay? So that's really what we can accomplish. And what I want to do is turn this over to Aryan, who's going to tell us about a simple Primal-Dual algorithm that comes very close to accomplishing this. And he's going to say a little bit about the software that we built to actually accomplish exactly this number. Why don't you use the mic? You can just use the mic.
Hello, everyone. I'm Aryan Kajandi, and I've been working on this problem for the last couple of years. And before I actually get started, I'd like to reiterate what Vivek said earlier about how thrilled we both are to be here today and presenting this work to you guys and sharing it. So I'd like to sort of recall what happens when an order comes in at time t. We essentially have a set of supply nodes from which we could fulfill the order. And associated with each of those nodes is a certain reward, right? So we said that if we fulfill the order from the jth node, the reward is RJT. So it's quite natural to try to want to maximize these rewards. And what we wanted to do in our formulation was something that's very familiar for everyone here, is we wanted some way of capturing the trade-off between reward that's earned, that's realized on this particular assignment, and the impact that that decision has on future rewards. So in assigning, we want to look at not only how lucrative it is to fulfill an order from a given store, but also how does that sort of compare to the value of inventory at that node? In other words, what's the opportunity cost of using that particular unit of inventory at that node, which could potentially have been used for a future order? And so motivated by this, we maintain these dual variables, right? So for each store, for each node J, there's a dual variable at time t, lambda JT, and roughly speaking, this this represents our estimate of the value of a residual unit of inventory at node J at time t. And so once we have this, it's very natural that to fulfill the order at time t, we want to pick a node, we want to pick an eligible node that maximizes the difference, that maximizes RJT minus lambda JT. And so then the question becomes one of essentially how to update, as we see more and more of the order stream, how do we want to update these lambda Js? And the update that we used is actually a pretty simple one. And let's walk through essentially what it entails, right? So this term here, the second term on the right-hand side, this is the actual realized value of that unit of inventory that we just used to fulfill the order with some scaling, right? But it's the actual realized RJT for the optimal node. This term is essentially keeping some of the history of the values that lambda J has taken in the past. And so the result is that at time t, lambda JT will be an exponentially weighted sum of all the rewards accrued as a result of assignments to node J. And it turns out that actually with this problem formulation and this pretty simple dual variable update, we can prove a pretty powerful performance guarantee for our algorithm. In particular, let's say B bar is the minimum initial inventory across nodes, and let's set these algorithmic parameters, the details. We don't have to parse those details too closely, but let's set these in a particular way. For a particular setting of alpha 1, alpha 2, and beta, we have the following result. We have that this Primal-Dual scheme achieves this competitive ratio. And my claim is that this competitive ratio is actually within a constant factor of the optimal, of the best competitive ratio that any online algorithm can achieve. right? So the first term there, 1 over 1 plus log kappa, you'll recall from Vivek's piece earlier that that's a bound on the best achievable competitive ratio for any online algorithm. And so we're only off by the second term, this e kappa minus 1 over e plus 1 kappa minus 1. And if we look at that term, it turns out that it's basically a constant. It's bounded by a constant. So for large kappa, it's going to tend toward e over e plus 1. And for kappa equals 1, which is sort of the smallest value that kappa can take by construction, it's going to be 1 minus 1 over e. So this rather simple dual variable update in this problem formulation actually ends up achieving very close to optimal results with respect to the best possible online algorithm. And before moving on, I want to mention one other thing, which is that we discussed the kappa equals 1 case representing the AdWords problem. If we set kappa equals 1 here, we actually recover. The first term goes away, the second term goes to 1 minus 1 over e, and we actually recover that same AdWords result. Now, this is a very powerful theoretical guarantee. We're very happy about it. But in reality, it may be the case that B bar, for example, might not be large. And so some of the approximations that are made in arriving at this performance guarantee might not hold. So it's very important, and it's very easy to see why B bar might not be large, because Vivek talked about how we're operating in a low transaction count setting, and that's very often correlated with a low inventory setting. So it's very important to see how that applies in practice and how that might impact how we want to tune some of these other parameters. And so Vivek will talk shortly about how this algorithm performed in our experiments and also in the real world. But before we get to that, I want to take just a little bit of time to talk about the software architecture that we use to implement this algorithm. And I want to do so because it's actually a very non-trivial problem. So we discussed earlier, right, that in this context, our system needs to scale to handling on the order of 10,000 orders a minute, which means that if we were doing this in a single-threaded manner, we'd have just 6 milliseconds to make a decision on each order. And that's clearly impossible because network latency, database reads, those alone will take on the order of hundreds of milliseconds. And so we would need something like 17 parallel threads to even begin to make this work. But it's not immediately clear that works out of the box either, right? Because the problem it's not embarrassingly parallel. In particular, those 17 parallel threads that we would hypothetically want to implement would have to share significant state. So the way we've described the algorithm, it's sequential, and so those threads would have to share dual variable state, and they would have to share inventory state. And sort of failure to account for that state sharing could very easily result in suboptimal or even infeasible fulfillment decisions. And the solution that we sort of came up with for this is what we're calling speculative fulfillment. So it's in the spirit of speculative execution, with which most people here, I imagine, are familiar. And the idea is that in each of these threads, we're going to act as if executing against the cached state that we see is actually the right thing to do. And then we'll have an independent process that goes through and detects any errors and rolls back those changes. And what we find is that essentially this allows us to capture almost all of the gains from that parallelization while having this sort of safety, this sort of guardrail that prevents, that catches and corrects any algorithmic or feasibility errors before the decision is sent to the node. And with that, I'd like to give the floor back to Vivek to talk about some of our experimental and real-world results. Thanks.
So I have a couple minutes. And so to use that effectively, I want to highlight just 2 things. OK? So let me actually accelerate through this and really just kind of point at this little experiment over here. It's a bunch of numbers, but I just want to draw your attention to the middle column over here that says lost sales. OK? So this is an experiment that was run against slightly obfuscated data traces, where we actually knew what true demand actually was across all channels, and we deliberately underallocated inventory. Okay, to understand exactly what could go wrong. Remember that what we're after is effectively bringing COGS down. Now, when we actually bring down that inventory and you try and run what we're calling baseline over here, which is effectively a greedy algorithm, as I mentioned earlier, you lose on the order of 12% of your demand. Okay, so your lost sales is on the order of 12,000 units, which if you look at the total demand in this setting is roughly about 12%. Now, one of the things you could do is say, listen, if you were clairvoyant and you got to see all of the demand in advance, what would you actually get, right? And remember I said we deliberately underallocated. So what we get to over here is something where you're losing on the order of 8% of your actual demand, but there's no way to escape that, right? This is literally with the best possible allocation after the fact. And the question becomes, great, so between 7,000 odd or 8,000 odd lost sales and 12,400 lost sales, where would we actually stack up, right, when we run this forward? And the short answer is we capture about 85% of these savings. Our lost sales are in the order of 8,500 units. Put a different way, you get to kind of capturing about 85% of the gains from perfect pooling. Okay, and that was sort of the big number for us. Of course, we looked at this many different ways, but this was sort of a key thing. And just to end, what I'd like to leave you with is the fact that, as I said, this was motivated at Urban Outfitters, which is a specific retailer. It turns out that we were able to get this to work at a whole bunch of other places. And in fact, give me one quick minute.
Spreadsheets can't be real-time. When the orders are coming in by the thousands every minute,
so
you need a responsive real-time system.
Thank you. So let me actually pause this, right, just to stick with the thing. This was meant to be the folks at Aldo talking about really a completely different retailer, talking about how they got this to actually work over there. But with that, I'm sorry about that, Patricia. Go ahead.